Okay, we're going to talk about accelerated motion now. So here's what we've been talking about before. We're going to have our time distance graphs, and here's an object that's traveling at a constant velocity. As time goes on, distance increases. Okay, we could draw the same object on a velocity time graph now, where it would look something like this, where the velocity is not changing. It's moving at a constant velocity. So let's say this is 3 meters per second, and as time goes on, this object stays at 3 meters per second. So the slope of a distance time graph here would be meters per second, which gives us that velocity. So let's say this slope is 3. Then what that means is that the velocity of this object is 3 meters per second, and the corresponding velocity time graph would look like this. Okay? If a velocity time graph looks like this, we have increased velocity over time, we have an acceleration. And to find the acceleration, we do the slope again. So this time the slope would give us rise over run to be meters per second, which is the same thing as meters per second squared, which is an acceleration. So the units can help you understand how to use a graph for something helpful. In this case, if we have a velocity time graph, the slope is the acceleration. That's something we might want to know. Okay? So the acceleration, it's the rate at which the velocity changes. All right? So our average acceleration is change of velocity over change in time. And we can write that as final velocity minus initial velocity over time final minus time initial. Instantaneous velocity is obviously, we're going to need calculus for that. We would need to take the derivative of a velocity function in order to find an instantaneous rate of change at a specific point, which we're not going to be doing because you don't know calculus yet. All right? Here's an example then. Let's say a hockey player glides along the ice at a constant speed of 1.25 meters per second in the positive direction. And then they hit a rough patch of ice which slows him down. If he stops in 5 seconds, what is the magnitude and direction of the acceleration? All right, to solve this problem, we know that average acceleration is the change in velocity, which is velocity final minus velocity initial, over the change in time. They told us that the change in time was 5 seconds, so we can plug that in. They told us that the final velocity is going to come to a stop. It says if he stops in 5 seconds, so final velocity would be 0. Initial velocity is 1.25 meters per second. And that would give us our acceleration of negative 1.25 over 5, which let's write as negative 0.25 meters per second. Okay, so the magnitude of our acceleration is 0.25 meters per second. The negative sign, we could say that's their direction, so we would say they're decelerating or just accelerating in the opposite direction of motion. Opposite direction of motion. So that's important to know that when an object is slowing down, right, so say the object's traveling this way and it hits this rough patch of ice, the acceleration vector, it's actually accelerating this way, opposite to motion. So even though the motion's going this way, it's accelerating the opposite direction. We're going to talk more about that. All right, let's look at the acceleration of a sprinter here. If we have a velocity time graph like this, a sprinter starts off, and the velocity isn't very much, but the slope here is fast because at the beginning the sprinter is accelerating very quickly. Over time, the velocity increases and the slope, the acceleration is the slope, is decreasing. So over time the acceleration, they're not changing velocity as much, they reach full speed. And when they reach full speed, there's no more acceleration and the velocity's reached its maximum value. All right? Here is if we take this equation, final velocity with average acceleration, all right, we can use it to solve other types of problems like this. Let's say a golf ball rolls up a hill towards a miniature golf hole. Assume that the direction towards the hole is positive. If the golf ball starts at the speed of 2 meters per second, slows at a constant rate, what's the velocity after 2 seconds? So once again, we're going to use the same formula. Average acceleration is velocity final minus initial velocity over change in time. So this time they give us the acceleration. Let me just plug all this in down here. They give us, starts at the speed of 2 meters per second, so that's going to go here. It slows at a constant rate of 0.5 meters per second squared, so that's an acceleration that I'm going to put here. What's the velocity? So we want to know the velocity final after 2 seconds. So we're going to plug 2 in here. I'm just going to solve this for velocity final. Multiply both sides by 2, in which case I get 1. Equals velocity final minus 2, add 2 to both sides, and the final velocity is 3 meters per second. Okay? What's the golf ball's velocity if the constant acceleration continues for 6 seconds? So now we're just going to change this denominator to 6. So when we multiply this, we get a 3 here instead, and then when we add the 2, we get 5. So now it would be 5 meters per second. All right? And then describe the motion of the golf ball in words and with a motion diagram. All right, so we've got a speed to start. It's slowing at a constant rate. And I made a mistake here, and I should have caught this right away, but this 3 meters per second is wrong, and so is this 5. And the reason why is because we know that it starts at 2 meters per second and it's slowing down. So our final velocity shouldn't be faster than the original if it's slowing down. That was just a no-brainer. What I did wrong here, is I didn't consider the negative here. Acceleration is in the opposite direction of motion, so the acceleration value should have been a negative right here. So when I multiply both sides by 2, I get -1 equals final velocity minus 2. When I add 2 to both sides, I get final velocity equals 1. So the first answer should have been 1 meter per second right here. And the second answer, when I stick in 6 down here in the denominator, this should have been a -3. And then this would have given us, add 2 to get -1 meters per second. So it actually been going in the opposite direction now. So it would slow all the way to a stop. And be coming backwards back at us. All right, so describe the motion of the golf ball with words and with a motion diagram. I'll do it with words verbally here and then a motion diagram, but we've got a golf ball here. It's rolling up a hill, all right? And as it rolls up the hill, it's slowing down, so our motion would look like this. Okay, where these points are getting closer together, all right, to the point where it completely stops and actually starts rolling backwards. Okay, that's what a motion diagram would look like here. All right, let's look at a velocity time graph again, and let's use it to find the displacement. Okay, so the nice thing about a velocity time graph is we can find distance or area underneath the curve, and that will give us distance. So this question says, use the velocity time graph, find the displacement of the airplane at change in time of 1 second and change in time of 2 seconds. All right, so change in time of 1 second would be this area right here. And the reason I know to use area to find distance in this case is because distance is velocity times time. Right, so I know that if I take velocity times time, I'm talking about a little unit of area on this graph. And if you look at the units will help you. On the graph, we want meters per second times seconds in order to give us meters for distance. So the units will also be very helpful in determining what to do from a graph. In this case, I want meters per second times second, and to get meters. In this case, I want my change in time is 1 second times 75 meters per second. And then you'll get 75 meters. That's the area right here, and that represents the distance traveled from this airplane in the first second. After 2 seconds, obviously, we're going to double that, and we're going to end up with 150. All right, so let's look at then position with average acceleration. Our distance final equals our initial distance plus initial velocity times time final plus 1/2 average acceleration times time final squared. The order doesn't matter in the way we write these terms, so sometimes I'm going to start with, put it in standard form the way you learn, because this is a quadratic relationship. And we put these in standard form in math class where we put the highest exponent first. So I'll probably follow that pattern mostly. All right, so we could also combine the last two equations and come up with a new equation for velocity with constant acceleration, which is right here. Velocity final squared equals initial velocity squared plus 2 times the average acceleration times the change in distance, which all these formulas are on your formula sheet. If you pull this up, you're going to see under kinematics I'm giving you all these formulas. So what I just gave you is these last two right here. All right, let's solve a problem now. Let's say that Joni jogs at a velocity of 2.5 meters per second. If she then accelerates at a constant -0.1 meters per second squared, how fast will she be jogging when she has moved 10 meters? What I do to solve these problems is write down everything that I'm given. So I'm given an initial velocity, in this case, of 2.5 meters per second. Okay, I'm given an acceleration of -0.1 meters per second squared. I'm asked to find how fast will she be jogging, so I'm asked for final velocity. and the distance I'm given is 10 meters. Then what I do is I look at my formula sheet and say what formula would help me solve for missing variable. In this case, this is a relationship that involves those quantities. So I've got final velocity squared equals initial velocity squared plus 2 average acceleration times change in distance. I'm looking for final velocity. I have initial. This is negative 0.1, and the change in distance is 10 meters. Okay. Now, that's final velocity squared, so I can't forget to square root that after I get the answer. But if I simplify this, I get 4.25, and then if I square root both sides, we get our final velocity is approximately equal to, we're going to have to round this, 2.1 meters per second. I'll round to the nearest 10 to stay with the significant digits of my least precise measurements here. All right, so, and they did give us 0.10 here. Just followed with the correct sig figs. So final velocity in this case is 2.1 meters per second, which makes sense. We're slowing down, right? So we started off at 2.5 meters per second. We end up at 2.1. Okay. Next, let's say we're driving a car traveling at a constant velocity of 25 meters per second. When you see a child, we're going to run the road, and it takes us 0.45 seconds for us to react and apply the brakes, and then the car is going to start accelerating in the opposite direction of 8.5 meters per second squared. So I put negative because I know that acceleration is in the opposite direction. It's going to come to a stop, so the final velocity is going to be equal to 0. This is my initial velocity up here when I start that stop. What's the total distance? So the question is, what is the change in distance? Well, I can use the same formula. Final velocity squared equals initial velocity squared plus 2 times average acceleration times change in distance. And this time I'm solving for the change in distance. So final velocity is 0. Initial velocity is 25. Average acceleration is negative 8.5 times the change in distance, in which case I'll subtract 25 from both sides. 2 times 8.5 should give me negative 17. Divide both sides by negative 17, and I get the change in distance is approximately equal to 1.5 meters. Okay, so if I'm going 25 meters per second, and I can stop, slamming on the brakes, I can stop pretty quickly. I should only travel about 1.5 meters. But what I need to add onto this is my reaction time. It took me 0.45 seconds traveling at a constant speed. So my distance equals velocity times time is also something I need to add on there for the constant part, my reaction. Before I apply the brakes, I had constant motion. And that distance is velocity of 25 meters per second times that reaction time of 0.45 seconds. In which case, that gives me a distance of 11.25 meters. So really I need to add these together. 11.25 and 1.5 gives me 12.75 meters of total distance traveled before I can come to a stop. All right, a couple more things. Once again, here's my velocity vectors to represent a car that's decelerating or accelerating in the opposite direction. If you slam on the brakes, you've got constant velocity while you're reacting. Once you hit the brakes, the velocity is decreasing, so you see these velocity vector arrows get smaller. And all the while, the acceleration is the same in the opposite direction during braking anyway. It's opposite to motion. Okay. All right. Next is free fall, and I'll cover that in the next video.